Hello! Today we are going to go through two problems from 2014 AP Chemistry FRQ. We are going to do numbers 2 and 7. So let's begin. Number 2. Propanoic acid CH3CH2COOH is a carboxylic acid that reacts with water according to the equation above. At 25 degrees Celsius, the pH of a 50 milliliter sample of 0.2 molarity CH3CH2COOH is 2.79. So we need to identify a Bronsted-Lowry conjugate acid-base pair in the reaction, and we need to label which is the acid and which is the base. So when we look at this equation, we can see that the CH3CH2COOH loses an H when it turns into CH2CO-. This tells us that this must be an acid and this must be a base, so we can label them as such. Similarly, there needs to be an acid and a base on each side, so we know that H2O must be a base and H3O plus must be an acid. Okay, so B. Determine the value of Ka for propanoic acid at 25 degrees Celsius. Well, we know that the formula for Ka is the concentration of products over the concentration of reactants. When we look at the equation, we see that there is a liquid, H2O. We can't include liquids or solids in this equation, so we can omit that from this equation. So we find that it is equal to the concentration of CH3CH2COO- times the concentration of H3O plus over the concentration of CH3CH2COOH. So what are the concentrations? Well, we know that the concentration of H3O plus is equal to 10 to the negative pH. And we know that the pH is negative 2.79. So if we calculate that, we can see that it is 0.0016, and we can change that to 1.6 times 10 to the negative 3 molarity. And we know that the concentration of CH3CH2COO- is equal to the concentration of H3O plus. So, okay, so then what is the concentration of CH3CH2COOH? Well, it is 0.2 molarity minus this concentration. And because this is rather insignificant, we can say that the concentration of CH3CH2COOH is just 0.20 molarity, right? So after that, we can just plug that into this equation right here. So that would be 1.6 times 10 to the negative 3 squared over 0.2. So we take this, we square it, and then we divide by 0.2. And this turns out to be 1.3 times 10 to the negative 5th. So that is our Ka value. Okay, so C. For each of the following statements, determine whether the statement is true or false. In each case, explain the reasoning that supports your answer. I. The pH of a solution prepared by mixing the 50 milliliter sample of 0.2 molarity CH3CH2COOH with a 50 milliliter sample of 0.2 molarity NaOH is 7. Okay, so we can see that that is false, because the conjugate base of a weak acid undergoes hydrolysis. As seen in this equation, it combines with H2O to form CH3CH2COOH and OH-. This creates a solution with a pH that is greater than 7. So that is false. And 2, if the pH of a hydrochloric acid solution is the same as the pH of a propanoic acid solution, then the molar concentration of the hydrochloric acid solution must be less than the molar concentration of the propanoic acid solution. So this is true. We know that HCl, hydrochloric acid, is a strong acid and it ionizes completely, as its definition determines. Fewer moles of HCl are needed to produce the same amount of H3O plus ions as the propanoic acid solution, because that only partially ionizes. A student is given the task of determining the concentration of a propanoic acid solution of unknown concentration. A 0.0173 molarity NaOH solution is available to use as the titrant. The student uses a 25 milliliter volumetric pipette to deliver the propanoic acid solution to a clean, dry flask. After adding an appropriate indicator to the flask, the student titrates the solution with a 0.173 molarity NaOH, reaching the endpoint after 20.52 milliliters of the base solution has been added. Okay, so D. Calculate the molarity of the propanoic acid solution. Well, we know that it's at the endpoint, so we can just use this formula. The MA is equal to MB times VB over VA, where M is the molarity and B is volume, because we know that the moles of H plus is equal to the moles of OH minus at the endpoint. So then we can just plug in the values. And then we can solve. So we can see that the answer is 0.142 molarity. Okay, so the student is asked to redesign the experiment to determine the concentration of a butanoic acid solution instead of a propanoic acid solution. For butanoic acid, the value of pKa is 4.83. The student claims that a different indicator will be required to determine the equivalence point of the titration accurately. Based on your response to Part B, do you agree with the student's claim? Justify your answer. So from B, we can tell that the pKa is the log of 1.3 times 10 to the negative fifth, so the pKa is 4.89, which is really similar to this pKa of 4.83. So we have to disagree with the student's claim. Because it's really close, the pH at the equivalence point in the titration of butanoic acid should be really close to the pH in the titration of propanoic acid, so the original indicator is appropriate for the titration of butanoic acid as well. So let's go on to number 7. The half-life of the catalyzed isomerization of cis-2-butene gas to produce trans-2-butene gas, represented above, was measured under various conditions, as shown in the table below. A. The reaction is first order. Explain how the data in the table are consistent with the first order reaction. Well, for a first order reaction, the half-life is independent of reaction concentration or pressure, so we can see this in trials 1, 2, and 3, because the values for the half-life are constant. B. Calculate the rate constant K for the reaction at 350 Kelvin. Include appropriate units with your answer. Well, we know that the formula for a K is 0.693 over the half-life. So we can just... And this half-life is 100 seconds. So that's basically... And this is 1 over seconds, so that's the same thing as seconds to the negative 1. Okay, so C. Is the initial rate of the reaction in trial 1 greater than, less than, or equal to the initial rate in trial 2? Justify your answer. Well, the initial rate in trial 1 is less than that in trial 2, because we can see that the initial concentration in trial 1 is less than that of trial 2. but the K value remains constant. D. The half-life of the reaction in trial 4 is less than the half-life in trial 1. Explain why in terms of activation energy. So the temperature is higher in trial 4, as we can see, 365 as opposed to 350. So the average kinetic energy of the molecules is greater. Because the temperature is greater, there are more collisions. So the greater number of collisions give the molecules more energy to overcome the activation energy barrier. So the rate is greater. Okay, so that's it. Thank you.